Here.
Well, good afternoon, everyone. Whenever we okay to go.
I think so.
I thank you all for joining us today on Thursday. We have two exciting guests replacing one. Well, we could say he's not as exciting because he's not here, but Eddie Saab is the president of Westinghouse, Canada, and he is getting in very late tonight. But the two senior directors that you have here are just incredible with their expertise and technical acumen on everything related to clean energy. Today's focus is going to be on the micronuclear project and Westinghouse's eVinci technology. And Michael Valore will be speaking to that. And we will also have a presentation on long duration energy storage, a must needed component to renewables as we go forward with a more clean energy agenda for us here in. Robert, why don't you come up here first and start with long duration energy storage?
I used you know. Yep. Just do the hamburger menu. You should have it up. Over very far away.
Oh, yeah. Gotcha. That probably looks okay the way it is.
Yeah.
We'll go this way. Let me jump down to my topic. Good afternoon, everybody. Thank you for the time today. Just gonna get to the right spot here. All right. I think there might be a person or two here who may have heard us speak a little bit earlier in the day, so I'm going to try to avoid too much duplication, but I want to talk a little bit about long duration energy storage and its fit globally into emerging energy needs, and in particular, its fit into Alaska. We've had a lot of conversations over the past few months here up in the region, very fruitful conversations and a lot of opportunity, I think, to solve some energy challenges in a novel way. I'm going to have to get a little creative with the scrolling since this is a PDF. We'll get right into the technology pretty quickly. We know we have an evolving grid. We know we have an evolving generation mix. That mix that's changing in different ways in different countries and different states. And the challenges that are presented at each state are a little bit different, but overall, we have a common problem set from non-dispatchable generation being added to the grid, mainly in the form of solar and wind. That's variable supply. It's a reduction in the overall system stability on the grid, and it's changes to the way that electricity is flowing from community to community, from city to city, and then over various transmission areas. Because we have less baseload power, less instantly on-demand power, and more power that's available only when it wants to be available. There's a whole host of ways we're going to solve these challenges. There's not one size fits all. We have a lot of talk about hydrogen. We have nuclear power, both in the form of micronuclear that Mike's going to talk about, as well as large baseload nuclear in a lot of parts of the world. Hydrogen turbines, lithium-ion batteries, and specifically, what's the acronym that's been accepted and kind of adopted in the industry is LDES, long duration energy storage, and it's defined as something that can store a large amount of electricity, discharge that electricity over multiple hours, days, or weeks, generally accepted at 10 hours or more of discharge duration. The other piece of LDES is that it's inherently different from lithium-ion batteries in that the power capacity of the system and the amount of energy that you can store are not directly coupled together. What that means is I have a certain amount of power capacity, costs a certain amount of money, and now I can add storage very cheaply to go to 5, 10, 15, 20 hours over time. Let's see, we'll go to the next.
And Rob,
Yes.
this group is very interactive, and I know you wouldn't mind if any people ask questions
Yes.
as you're going forward with the
Yeah, please.
presentation.
Feel free to interrupt me and ask any questions, certainly, at any point. The LDES market, again, we're talking non-battery, long duration storage. It's been a challenge because outside of pumped hydro, you don't have any technologies that are really deployed at mass scale. Pumped hydro is wonderful. It's a great solution, but permitting and costs make it very difficult to deploy much more pumped hydro than we have today. And when you look at the storage needs that are projected by many different agencies and consultants and governments, at the end of the day, you're looking in the 2030s of probably 1,000 megawatts, or sorry, 1,000 necessarily you have a situation where you need to catalyze the industry, and that's where the Department of Energy has come in. The U.S. government. Back on?
Yeah.
Okay. And so we've been looking at these programs. So the Inflation Reduction Act, for example, current DOE programs out of the Office of Clean Energy Demonstrations, they are providing significant discounts and ways to de-risk projects so that you can have current adoption of these technologies. And that's what we've been looking at in Alaska. We've been looking at it in other places, but we're seeing a lot of activity in this area, and it's not just in the type of solution that I'll get to in a moment that we have. It'll be a mix of solutions. It'll be much like we have a lot of generation sources. We'll have a lot of different storage sources.
Rob, can I ask you to stop share and share again?
Oh yeah, stop share again, no problem. Where are we on Zoom here? Share screen.
There we go.
Back up and running?
Yep.
Okay. Well, talk for a couple minutes about technology that Westinghouse has been looking at deploying in Alaska. This was a system that had its inception about 10 years ago. We were looking at novel ways to store energy with nuclear power plants, coupled to nuclear power plants. So thermal energy storage in that case. And as we developed that thermal energy storage solution, we came to a place where we saw the future need to develop a standalone electricity in, electricity out storage, standalone storage solution. And that's what we have with pumped thermal energy storage. It's our drivers from the design were low cost, first and foremost, sustainability, inherent safety, something that can be scaled, and something that wasn't a science experiment, something that was primarily based on existing and known technology, known components, things that we have in our existing supply chain today as an energy company that we could put together in a novel way and create something that was able to store energy in economies of scale that hadn't been realized. Our target was to be better than 30% cheaper than lithium-ion batteries. That's at a 10-hour duration. I'll show you in a moment how the system works, but I will note at 10 hours, we're about 35% cheaper than lithium-ion with pumped thermal energy storage. As you go to 20 hours, as you go to 30 hours, that gets better and better. And I'll explain why in a moment, but it's because the cost of the storage medium is so inexpensive. And I'm going to skip to the next one and I'll talk through how this system works because it's the more interesting part. And I'll preface this with, this might sound very simple. In fact, it is pretty simple. It's actually as simple as it sounds. But what you see here is it's a 100 megawatt, 10-hour facility. So 1 gigawatt hour of electricity storage. And you have 3 main systems. You have on the bottom left, you see a building with some equipment in it that's cut away. That's essentially a turbine building like you'd find at any gas plant, simple and combined cycle gas plant. There's a turbine, a generator, and a large compressor. Then I have a large water tank, which is a cold reservoir. And I have some elongated oil tanks with concrete modules that are submerged in the oil. And that's my high temperature reservoir. The way we operate this system is we're running it's an electrically driven heat pump. And it's a supercritical carbon dioxide heat pump versus a typical refrigerant you'd find in your AC system or using air as a refrigerant. Supercritical carbon dioxide gives us some interesting properties. It allows us to work at interesting temperature ranges and relatively low temperatures. So we operate that heat pump and we simply pull heat out of the water and we pump that heat into the concrete. So we're moving, it's like a heat pump in a home. We'll move heat from inside to outside or vice versa. We're moving heat from a cold reservoir to a hot reservoir and creating a thermal differential there. When the system is, once you've moved all the heat, you now have a state where I have essentially a frozen or an ice slurry in a big tank, and I have concrete that's at 330 degrees C. I'll just mention for a moment that the concrete solution, it's not a new idea by itself. There's companies that try to store heat in bricks, in volcanic rocks, various mediums, gravel, for example. We simplified, this is where Westinghouse developed some patents and a bit of technology in terms of eliminating anything like heat transfer tubing, any complex mechanisms. We have engineered concrete modules that go directly in a tank, and we're simply pumping hot oil in one end of the tank and out the other, and everything is designed where that actually builds a thermal wave through the concrete, heats it up appropriately with again, minimal equipment. You're talking about ambient pressure, mineral oil, and fairly standard concrete. It's a somewhat engineered mix, but it's nothing terribly exotic. Once I pump that heat from one end to the other, and I want to generate electricity, I simply have that heat run back through the supercritical carbon dioxide system and running as a heat engine. Spins a turbine, spins a generator, generates electricity back onto the grid, and rejects heat back to the ice, which now melts back to water, and I'm back to my starting state. So that's the simplicity of how the system works. There's a little bit more going on underneath the surface, of course, but maybe I'll pause, see if there's any questions on the operation of that system.
And there's no radiant waste.
No, it's all insulated, it's all closed loop. That's correct. Yes, Robert.
What's the leakage rate?
Heat leakage, about 0.5% per day.
So it's insulated well enough to-
Correct. And what you actually end up doing, you lose about 0.5% a day of heat on the concrete side, and you put a small heater that keeps it topped off, and it shows up as a house electrical load versus a heat loss if you want to do it that way. So I'll have no heat loss, and I'll just have a small incremental house load on my electrical system. But if you let it sit there with no extra heater, it'll lose about 0.5%.
And we have
when it froze. Can you hear me? I don't know if Winetta froze or not. I don't hear you.
say that, that system is fully charged. What's the effective parasitic load on that facility? It just sits there and not being called on.
If it just sits there, it's just the parasitic load is actually, besides the leakage on the INC systems to maintain their power, which is very, very minimal. It's only that heater on the concrete side, which is less than 0.1% of the electrical load of the plant. It's very, very small, surprisingly so, especially if you're idling, right?
What would be, let's say that you develop a pilot project, what would be the size, the capacity?
So yeah, I'll give you a range and then I'll give you a little bit more of a definitive answer. The smallest where we want to go is 25 megawatts. If you ask me what the limitations of this system are, it's that it's not going to be a solution for small sizes. 5 or 10 megawatts of capacity, it's not going to make the most sense. It really makes the most sense at 100 megawatts and larger. 25 is about the minimum where the economics may work out, especially for a pilot. We're looking at the ones that we're looking at right now, including one in Alaska as part of a DOE program. That's a 100 megawatt system that we're looking at. 100 megawatt, 12 hours. So it'll be 1.2 gigawatt hours of storage.
Where are you looking for?
Outside of Fairbanks.
Is that local or?
Healy.
Yeah. Okay, repurpose it.
Yeah, they're going to close Healy too. So put this in there and help out. That's the thought. Yeah, yeah. Yeah, the one that's staying is old. The nice thing is this integrates well into an existing plant because it looks and feels a lot like a power plant, right? It's the same type of equipment at a gas and coal plants. It's tanks, it's piping, it's rotating equipment. It's pretty easy to integrate into the operations of an electric utility. It's really there's nothing here that any technician or engineer who's worked at a power plant wouldn't have worked on before. The main difference is the turbines. The SCO2 system is much more power dense. So a 100 megawatt turbine would fit. If you flip that large screen on its side, it would fit on that screen. Be that small.
No problem connecting to the grid at all?
No, just a regular GSU, regular step-up transformer like you'd have anywhere else. Yep. Actually, reuse the existing one if it's the if it's the right voltage. Yep.
What is the turbine?
Turbine looks like a typical turbine, just a little bit smaller, and the blades look a little bit different. I don't have it in here, but there's some images we could follow up and give you. But they're very small, and SCO2 turbines are. It's interesting. They actually like size more than they like being small. So as you get the challenge with small SCO2 turbines is they're extremely high speed. Once you get up to this size of 100 megawatts, you're talking 3,600 RPM, like a standard 2-pole machine at a lot of coal plants and any gas plant.
Your box between the turbine and the generator?
Yeah, yes, yep. Probably not direct coupled, depending. I mean, it depends on the generator, but you may be able to have at 100 megawatts, you could probably have a direct coupling like you would at a standard power plant. The equipment is, yeah, it's not. I know what I was going to say. You made me think of something. The nice thing about this is it also provides you grid support. So those ancillary services, you got rotating inertia on the grid. I can provide reactive power support. If I'm not charging or discharging, I can just run this as a synchronous condenser and provide reactive power support onto the grid, right? I can clutch the generator over to a motor and just provide support. So it's got a lot of good characteristics in terms of stability, as we were talking about, Robert. But you have all these solid state devices and solar panels or batteries, other things. Your stability levels going down. This can bolster that.
So any word on the predicted cost per kilowatt hour?
For the first couple articles at the 100 megawatt size, about all in cost, about roughly $300 a kilowatt hour. And we're actually working with the DOE on these on those numbers. Once you get to nth article, $220 a kilowatt hour. And that's future state, future cost. And that's for 10 hours. So if I need 20 hours, that number goes down. That's the high end. Because if I want to take this system that you see and turn 10 into 20 hours, I just need more water, oil, and concrete, which is the cheaper part of the system.
So, we, last year we did a lot of earthquakes, and we done a lot of concrete. You have any concern about that?
Luckily, so the concrete's not really poured. It's a little bit different. And two parts to that answer. One is we design nuclear power plants to withstand earthquakes. So the seismic design is not a concern for us. And number two, the way that this concrete is designed, it's not poured in the ground. It's going to be in this oil tank. The oil tank is what has to withstand an earthquake. The funny thing is, if you crack those concrete plates, you actually improve your performance. As long as you're not turning them to dust, you just get more surface area, better heat transfer to a point. So actually, if they crack over time, you don't take a performance hit. It was part of the interesting design that came about as we were going through it.
You should break them on purpose.
Well, we've had that. There have been engineers who have said we should cycle it at first and crack them a few times and then go into it. But
I think Barbara has a question.
yes,
Go ahead and
please.
open your mic, Barbara.
Hi, yes, I'm very interested in this concrete component because you say this is something that's being proposed for replacing Healy 2?
Yes,
That concrete component is
not
of
replacing
interest.
it. Oh, sorry. Go ahead.
That concrete component is interesting to me. In Fairbanks, we have a building made of concrete, and apparently it has to be dismantled piece by piece because the concrete is full of PCBs. And then it has to be shipped to the state of Washington. But it seems to me, if this is completely contained, could that building, those building pieces,
You reuse it.
yes, save us the trip to Washington?
So I knew where you were going with that. That is it. You know,
I looked at this and I went, oh, I know what to do with that building.
well, there are a couple ways you can design the concrete reservoir. It's not only with the plate design. There's a couple ways you can do it based on geography or space. It is something we could look into. There is a way you could probably break up that concrete and put it in a packed bed configuration. Depending on what type of concrete it is, we can test. You may be able to make something like that work. We could have engineers look at it.
Well, I think Mayor Pruz would be very interested in that possibility because that the EPA and Mayor Pruz have been struggling with this very big building in Fairbanks for a very long time. It used to have the Tiki Lounge on top.
Yeah.
When I'm up there tomorrow, I'll ask about it.
Chip off the sample.
Yeah, no, that's a very interesting idea. I'll note that. That's something we could look at.
Okay.
Thanks, Barbara.
I'm looking at the time. Give myself a couple more minutes and then we'll switch to Mike, I think. So I'll be quick here. And I kind of touched on some of these notes, but why I do want to say when you look at the long duration energy storage market, general consensus seems to be that early adoption over the next 5 years is going to be driven in areas like Alaska that have single point of failure grids, a lot of remote areas, trying to decarbonize somewhat. They're probably going to lead the pack versus a state like New York, for example. You've got heavy industry, military bases, mines up here that want to try to procure cleaner power. And this would significantly help them to do that, which is part of what we're looking at in our studies up here. But I also want to note it's not just for renewables. This is source agnostic. I can take energy from a coal plant, from a gas plant, from wherever it's coming on the grid, store it, use it as needed. It allows me to optimize the use of all my other fossil power generation a little bit. Better use profiles on the units I have, less maintenance, less breaking down, et cetera.
Yes.
Yeah, and I think we talked a little bit about the DOE. I won't go into detail on it, but we were just talking about the opportunity. We are looking up at the Golden Valley on this. So the DOE, the Office of Clean Energy Demonstrations, has a $350 million funding opportunity out right now. And they're going to be projects in different categories, but it's specifically geared towards non-lithium based technologies such as this one. We believe they're going to spread it across different technologies. So probably one flow battery type of technology, one mechanical storage type of technology, and one thermal based storage type of technology. And that's the approach we're taking right now in Alaska on that opportunity, but it's. It's due March 3rd. We're actively working on it right now. Yep. And now, you know, maybe we can include in that application, taking an old building and dumping it in and storing energy with it. So that might help our application.
Super green.
Yeah, that's right. I want to make sure I give Mike time. Any other questions? Yeah,
Are there ramp rates for charging and discharging?
it's about 10 ramp rate's about 10% per minute.
So,
So,
I'm on the energy storage standard committee.
Mhm.
I get to lead it, and that's one of the big issues there, and it's important on battery, on the lithium ion battery.
right.
It looks to me like this doesn't really,
This is,
care.
yeah, this isn't meant for your dynamic response real fast, right?
so you just gonna use it pretty much like a generator. You fill it up and as full as you can fill it.
That's right.
And then use it on a fairly continuous,
Yeah, use it kind of continuously. That being said, you may one day decide you want to discharge it for 4 hours and then charge it again, or 6 hours.
Yeah.
You can cycle this as much as you want, right? So there's no depth of discharge concerns, no cycling concerns. You can run it back and forth as much as you want, run it all the way down, all the way up. It doesn't affect it, but you're not going to be changing it every 5 minutes up and down.
But this unit could take the place of whatever constraining that you need to do on a main turbine unit within the system where
Correct.
you need a rotating.
Yep.
Um,
That's right. Yeah, you know, on the East
spare
Coast,
somewhere,
yep,
so it would be effectively
rotating. That on the East Coast, a lot of the utilities are looking at this for replacing gas peaking plants. They're trying to get rid of the gas peakers and keep the nuclear, coal, and other sources. And they want to store this thing up and then have that peaking capacity instead of firing up expensive oil or gas fired peaking plants. The way to get a bit cleaner than they have this. They're typically running those 6 to 8 to 10 hours, and then they put this right on the side of the old gas units. Okay.
Any other questions online for Rob? Go ahead, Barbara, open your mic.
Yeah, hi, have you heard of this Grid Reliability Interstate Group?
Yeah, I think so. It rings a bell.
I think
Yeah,
they're called
yeah.
GRIP.
Yes. Oh, yes.
Yeah.
Are you presenting, are you interacting with them at all on this?
We are interacting with them. They ran out of time for
Yeah,
the presentation.
yeah,
because-
we have been. We got some stuff in the future, I think, right?
Yeah, we do. And you're up in Fairbanks all day tomorrow, so we're kind of limited on
Right.
meeting schedule.
Yeah, so we may be able to squeeze something in tomorrow, but we'll be doing it in the near future.
Well, I think it's part of GVEA.
GVA is a member of the
Yeah.
reliability.
So that might be the group that you're presenting to.
And it's applicable because transmission avoidance is a big use of this kind of technology, right? As much as it is generation.
Well,
Certainly.
I think it's the 5 utilities, 4 or 5 utilities. And one of the things that they're focusing on is the variable energy and how it affects the intertie.
Right.
And the intertie comes right through Healy, so that
Right.
may be related to your project.
Yeah, I think, yeah, I know it's been a topic of discussion. That's correct.
Okay, thank you.
Thanks, Barbara.
Rob, you said this,
Pass off the mic, please.
you talked to like 10 hours or more, how long you can't go out?
You know, we modeled it up to 200 hours. Depends how much real estate you got, how much water, but practically for the next 5 years, I'd say after 48 hours, we'd be comfortable. We're looking at one in California for 24 hours. Probably go to 60 or so, but I think you got some scaling we'd want to do before we went bigger than that.
Okay, can you just briefly introduce yourself?
Yeah, so I'm Mike Valore, the Senior Director for Advanced Reactors at Westinghouse. Been really substantially working on eVinci now. Been up to Alaska maybe 6 or 7 times over the last few years. Really helping to, it's helped me a lot to assess what might be opportunities for eVinci, but also one of the last trips up, we started to get this idea about the energy storage side as well. Knowing that, has a lot of challenges, and then also with the BESS, we felt that might be a good fit. So really, it's been helpful just to be, real physically present up here to really understand the market, the potential uses, but for Westinghouse overall. But eVinci is our microreactor. So we've been developing this now for about 5 to 6 years. 5 megawatts of electricity, but it can also, we can capture exhaust heat from it. So operating in a cogen mode where we get about 200 degrees Celsius, and 8 megawatts thermal out of it, in addition to that 5 megawatts of electricity. Operate for 8 years continuously without refueling. And would actually like to get that up to 10 years before the first commercial units are delivered, but we have to do some additional testing on fuel to be. It came back, it's coming back. It's coming back. Yeah, so we're not even again.
I retired from Oceanside. They kept me on the part-time temporary, so that way I could keep my health insurance.
All right, I think we're back. Sorry about that, everyone. Looks like we're losing internet occasionally here, but so the microreactor, really nothing has changed now for the last few years since we've been, I've been visiting Alaska, and we've been continuing to build out the design, develop this reactor and its technology. But we're really proud of the accomplishments we've made over the last year or so on maturing the technology itself, but also now engaging directly with the Nuclear Regulatory Commission on this design. We'll talk a little bit about that. But basic technology, for those of you that have maybe not seen me present up here before, it's transportable design, 40-foot by 14 by 14-foot container. So it's oversized truckload, but it can be done by road. We prefer rail and water. It's just faster, a little bit easier. We did some logistics studies for Alaska. We confirmed we could deliver this reactor to Eielson Air Force Base. Coastal locations also able to be done. But really, we're delivering this system in 4 containers: one for power conversion, one for the reactor, one for the instrument controls cabinets, and then a miscellaneous container basically to fit the application. So, cable piping, maybe a small heat exchanger, maybe a small amount of batteries if we need to have black start capability at the site, or have ultra high speed load following the site. We can put this on a single unit on less than 1.5 acres with a building that's about a 60-foot square building. And really, we felt that small and above ground was critical for Alaska. A big construction site with some of the other designs that people are purporting to have out there, we saw it would just be really challenging, let alone an excavation into permafrost within a hot reactor that is inside permafrost. So, really focused on this market significantly. And another piece of this design that we really love is its transportability, which allows us to scale and meet the demand of a growing or even a shrinking site, like a mine site could be when it's reaching end of life. But this also allows us to not have to handle fuel on the site of operation. So we bring this reactor with the fuel inside it, and then after the fuel is spent, we take the reactor away with the fuel inside it. And so doing maintenance on this reactor, but certainly doing a refueling or a defueling event on a nuclear reactor in a very remote area, we just saw as being incredibly difficult, if not impossible. But how we were able to get down to the small size is we took a very different approach with this design than has been done on nuclear reactors up to this point. Reactors out in the world today require water to be pumped through them. So you have, all sorts of components to support the pumping of that water and ensure that in all sorts of different scenarios, you can continue to move fluid through a reactor. This design, though, when we looked at what could you make a microreactor economical for, we saw shrinking a large scale plant design down to a small one would not get you there from a cost perspective. Things tend to not scale linearly with size with regard to cost. So a small nuclear power plant that's the same, has all the same components as the big one, is going to be maybe very uneconomical. So the team about 5 to 6 years ago started to align on heat pipes for cooling of a reactor. And Los Alamos National Labs had been doing work on heat pipes for reactor cooling, and then they actually operated a heat pipe reactor in 2018, which was substantially for space. So when you consider power needs in space, you can't have lots of operators. It has to be extraordinarily simple. It can't be a highly complex mechanical machine, because doing maintenance on highly complex mechanical machines in space is extraordinarily difficult. And then from a size perspective, every pound of weight costs, depending on the rocket, it could be $500,000 to $1.5 million for literally like a pound of weight. So what we saw was this heat pipe design for space, which the labs demonstrated. We started to think, well, that's the way that you get a microreactor that you could actually feasibly put somewhere remote and then have it not have to require many, many operators, have a small construction site, and actually be able to fit it into a very small package. So this design only has heat pipes for cooling. There's no pumps, there's no valves. And it's actually, we call it a nuclear battery because it's very much a solid state type device. In almost all of its operational modes, with the exception of startup, shutdown, and very large load swings, there's no moving mechanical parts inside this reactor system. Only the power conversion system shaft would be rotating. And the way we accomplish that is really the only piece that moves on this is the control drums that you can kind of see one at the bottom. Those rotate if we really need to change reactor power. But even if we get a large load demand change, what actually happens is the heat pipes will self-modulate this reactor. So they're very much self-regulating with whatever the demand is on the power conversion side is how much heat they will take out. And the reactor will actually respond in power based upon temperature. So if we had a large load shedding event, for instance, we would be taking less heat out of the heat pipes. The reactor would actually heat up a bit, but then the reactor power goes down based upon temperature. So this will actually chase load quite effectively without even any mechanical moving parts. The shutdown rods are really only for a defense in-depth shutdown. So basically a backup system that's totally autonomous from the drums as a method of shutting down the reactor. And even if the control drums and the rods would fail, the fuel itself will maintain its integrity. It's a much different fuel design for advanced reactors now than what's in current plants today. Basically, it's a bunch of uranium kernels that are very, very small that are then coated in multiple layers of material, including silicon carbide. And that silicon carbide, the melting temperature of that material is higher than what the uranium can achieve. So it's from a safety perspective, from an operational, we really saw this is a dramatic difference from existing reactors in a way that supports economic deployment to remote areas. Heat pipes themselves, we've been building and testing these now for 4 or 5 years. The way they work is very much like a thermosiphon, but we use sodium for the working fluid. Heat enters one side, vaporizes sodium. On the other side, we're removing heat and that sodium vapor condenses and it travels on the inner diameter of the heat pipe in a fine stainless steel mesh straight back to the hot end of the pipe. So we have hundreds of these in the reactor, and they're each a unique individual reactor coolant system. So that from a safety perspective, a lot of advantages here as well, where these are actually sub-atmospheric pressure. And since there's hundreds of them and they're all individual, we're not subject to a single point failure of our cooling fluid like many reactors are today. R&D is substantially being done outside of Pittsburgh, Pennsylvania, where Westinghouse is headquartered, but this is actually our field services facility. But we're constant, you know, I haven't taken a photo of this floor for probably a year and a half. Some of you've probably seen it, but every week, stuff's in different places. But it's not even really worth taking another picture every week. So we're continually, you know, reconfiguring this for whatever we need it for. But what we've really accomplished since the last times I've spoken to this group, which was actually, I think, last summer or fall, we completed our first 12-foot heat pipe manufacture. So up to this point, we had been doing 4 feet, which, you know, our prototypic full-size reactor will be 23 feet. But 4 to 12, we really saw if you could make 12 feet and you don't have distortion and you don't have all sorts of other like manufacturing challenges, going from 12 to 23 is actually somewhat trivial. So we also wanted to go to 12 feet because we're going to operate a test reactor before we put any commercial reactors out into the world. And that test reactor is 1/5 scale in power, and it uses a 12-foot pipe. So we've started now to make nuclear safety related. Truly, we could sell these and operate them in a nuclear power plant if there was a licensed design, but they meet all requirements from our QA program. We're now making these. That's a picture of the first one with the engineers holding it, which was completed right before Christmas. Their deadline was December 31st. So you could imagine why they were incentivized to complete it before Christmas. But they got that done, and now we're just continuing to produce these 12-foot pipes at our exact prototypic dimensions, other than length. But we're able to confirm a lot of our manufacturing processes we're going to scale with what we did last year. The test reactor I mentioned, so that is not a cartoon, even though it's not obviously a real reactor on PowerPoint. That's actually is our 3D model, design model for our test reactor, which is going through its detailed design phase now. Test reactor will operate at Idaho National Labs in 2026, and that will really be the culmination of our design and licensing effort for this reactor. From there, we believe through some scaling analysis, which Westinghouse has done pretty much for every nuclear reactor we've ever deployed previously. You know, you never build a 1,000-megawatt reactor to license a 1,000-megawatt reactor. It would be difficult to do. But this is a true prototypic test reactor, except 1/5 scale, a little bit shorter, a little bit smaller in diameter. But that's going through final design, and then it will operate inside that EBR2 dome, which is at the Idaho National Labs. So we are working with INL now on the detailed design of exactly where we're going to put that reactor in the dome, the amount of shielding that it will need, and the exact schedule, as well as the licensing for the test reactor right now. We've had teams out at INL for months. I'm sure they'll like it more in the summertime. Licensing progress, so won't go through all of this, obviously, but just wanted to highlight we have now submitted 24 documents to the US NRC that cover key subject areas with regard to our design, how we will show the NRC that our design meets their requirements and can be operated safely. So some of the key items you've maybe heard about nuclear, like the emergency planning zone, the transportation, the refueling and decommissioning, seismic. So one of the questions was, you know, how do you deal with seismic? So we've actually submitted to the NRC already our seismic design methodology. As Rob mentioned, we're veterans in developing nuclear power plants for seismic. And for these really small guys, it's much easier. So if you imagine our AP1000 is 100-some feet tall. Seismic difficulty for design increases with height and width and size. This is a very squat, very dense building and reactor, right? 60-foot by 60-foot building. The reactor itself is extraordinarily dense. So we're very resilient to seismic, but regardless, we have to prove to the NRC that this design will withstand anything seismically that could possibly be thrown at it in the areas that we plan to deploy. So that's just one example. There's quite a few other areas that we've submitted now. The NRC has provided both informal and formal feedback, but the formal feedback's on the NRC website, it's public information. And the letters basically say they have not found any major issue with anything we've submitted to date. So now what these will turn into, and this is maybe getting a little nuclear licensing detail, maybe more than is necessary, but so those papers are kind of the primer to the NRC, to which they can say whether we're on track or not. Do they agree with our methodology? Do they agree with our testing program and how we plan to operate this reactor? And they'll say something like they have in the public letters, which is we haven't found any major issues. But they won't formally approve that because we haven't asked them to yet. But now that we have the feedback we've gotten, we are starting to submit these documents formally to the NRC, which then they will give a formal review and either a formal approval, we need more information, or much less likely a rejection. Westinghouse typically does not send anything to the NRC that we don't expect to be approved after doing a lot of work and discussion with the NRC. So we submitted our first documents in December for formal approval, and we'll have a list here that will go out through 2025 that will build based upon the completion of design and testing information that we received from our development program. And as each one of these areas is approved, it starts to build into a single document that becomes our licensing approval for the eVinci design itself. So we're doing this in a piecewise fashion because we feel the NRC will be much more comfortable with that. And it also is better supported by our design and development program, which heavily relies on physically building and testing things. Because we think that that's how you get the NRC to a place where they can approve an advanced reactor.
Mike, can you talk about some of the other names that we've been hearing here in Alaska and some of the shortcomings with some of their filings with NRC?
Yeah, so there's only been one true NRC application submitted to the NRC by a microreactor vendor. That was submitted by Oklo, and it was formally rejected in January of 2023. They went to a process more of trying to just send a document and go into the formal process first. Westinghouse could easily do that. We have a lot of design. We could definitely take that approach. We could have submitted a combined operating license application probably maybe 3 years ago. But the challenge with that is once you have a formal application in place, the NRC can't really have private discussion. It starts to turn into a letter campaign.
Mhm.
And the NRC, being a conservative body by nature, and rightfully so, right, we all want that, including us, they're in a place where these are very new technologies. And so to just send something at them, we didn't think was the right approach, to just send them a pile of documentation and hope that they can agree to it. So we are bringing them, again, we're doing a piecewise approach. We've been hosting them to our facility. We're inviting them to actually come see the testing that we are doing, such that they're seeing it in real life, they're getting the paperwork, and they can move with us in the process, as opposed to please approve my massive pile of documentation. Which, even for a technology that the NRC might be more comfortable with, would still be challenging. Yep. Last slide really for me is this is really our timeline that has not changed in the last 2 years since I've been coming up here, which is a good thing. But what we have done in 21-22 is some of the things I've mentioned before. We ran an electrical demonstration unit. We did that 12-foot heat pipe, which is a huge accomplishment for us, since that's really the key to our design. And now in 23, we're doing design and starting to procure materials for our test reactor. 24, we'll really start building that test reactor and its components. Then 25, 26, we'll be delivering the test reactor, installing it, operating it, finalizing our full-size reactor design. And then by 27, we see actual licensing approval from the NRC, as well as potentially the CNSC. So we're working with the Canadian Nuclear Safety Commission right now on the licensing approach and schedule that we can expect from that regulator. So, we still are driving towards this technology. And it's a fairly small device that can be replicated. We see after you have regulatory approval, we could start installations at customers where we're beginning that effort in the next few years in parallel with the completion of the technology. So similar to Rob, we are looking at some DOE FOAs in Alaska. There is one coming out for rural electrification. There's also one coming out for current and former mine land sites. And we have some very strong potential partnerships and approaches to those where you really, with a small amount of investment up front as supported by the federal government, we can properly assess sites and properly really begin to develop where could the first ones of these microreactors go in Alaska. And we really want to do that in the right way. We're not just going to go select sites and force this on people. We'll start engaging in the communities as soon as we get alignment with the different parties on potential sites for this reactor. The last thing I'll say, Air Force, we did send a proposal to the Air Force. I do think they're taking they're taking the wrong approach, in our opinion, to put an early technology out into the commercial marketplace. So they asked for just the vendor to commit to a price per kilowatt hour in January of 2023 for a technology that is obviously not over the finish line, has regulatory uncertainty. We believe we can overcome. It still has a lot of uncertainty. It's just not an approach that we would have recommended. But we did send in a proposal to the Air Force based on how Westinghouse views would be the right thing for both a vendor and the Department of Defense to deploy this type of technology.
So, just there's a question
Yep.
online. The test site is in Idaho.
Idaho National Labs, yes, U.S. National Lab site.
You like to go out there, inverter or rotating?
Rotating, open air Brayton cycle. It's basically a hot air jet engine.
The other one of your early slides, the company talked about fast load following
Yes.
capability. So if you've got solar or wind resources
Mhm.
tied to the grid at the same time, will it is fast enough if you follow that? You wouldn't need a battery, a lithium-ion battery there to.
The answer is it depends on how fast those load swings could be. If we're in an extraordinarily small grid paired with renewables, some battery support would likely be required. But it's not, we don't need hours of battery support. This reactor can load shed almost instantaneously. And depending how fast we expect those load changes to go, we might actually just keep the reactor at full temperature and modulate power with the power conversion system. Basically by opening and closing a bypass valve. Yeah, automatic controls. Yes. Yeah, the operator, it's funny, we've planned an operator into all of our cost models. We're telling the NRC we'll have an operator on site. It's probably the right thing to do just from a security perspective and peace of mind perspective, but there's really nothing the operator can even do except manually shut this down. Like if they're operating to try to load follow by pressing buttons with this, it can't be done. There aren't even really buttons to press. Yeah, there's no, it's not like there's a system of pumps where you have to change, valve position. We just don't have any of those components really, which we see as a good thing.
All right, well, thank you. I don't see any other questions online and if anybody wants to type anything in, but Mary Ann, do you want to make a closing remark?
No, I'm just, this energy storage group has been active for quite a few years, and I think it's very exciting that we're seeing some of the changing technologies that are bringing solutions, not only here for the rail belt, but the remote parts of our state, for the mining opportunities, the industrial applications that we could have, and also that transition that's needed to augment and support renewables. So thank you all for listening today. Thank you to Rob and Mike for being here. I know they'll be back again because they love coming up with the snow and ice so much. Anyway, thank you all so very much. Juanetta?
That's it. Thanks, everybody. Thanks to our guests from Westinghouse. Thanks to everybody who's here in the room and everybody online. And we do have a couple of sessions that we're planning for March. We've asked for a repeat with Bernie Carl in the Macushin geothermal project in Unalaska. And we have a couple of other requests out there escaping my mind at the moment. But so stay tuned, watch your email, and we'll have more for you. Thanks for joining us. Thanks.